now have Mairi giving the second lecture on the topic of something about quantum gravity and cosmology, part 2.
Okay, so I'm going to pick up from where we stopped, I think it was on Tuesday. What we did then, I told you the success of the GR, why we need to go beyond GR, and then I highlighted some kind of elements of the main kind of approaches to quantum gravity. So now I'd like to go on and discuss the relation between these approaches and cosmology. So this is important from 2 points of view. From the one hand, because we'll be able to test these kind of proposals, because after all, if they try to model the universe in which we live, then we should have some predictions and then we should test them. And on the other hand, because we will be able to build cosmological models which are less ad hoc, they are motivated, inspired from a kind of fundamental theory. By doing that, we have to keep in mind that usually when we take this unknown full theory of quantum gravity and we try to find some predictions, we simplify the theory. So there is an important question to keep in mind: what is really the relation between the full theory that we do not know and the kind of more simplified version that we use in order to do cosmology. So, indeed, I believe that quantum gravity has as the unique test-bed cosmology. It is, of course, quite improbable to expect that ever we have a lab that will be able to go and test what's going on in energies of the order of 10 to the 19 GeV. That's what we need for the Planck kind of energy to be important. But as I write there, we are very lucky, because we live in the universe, we live in a big experiment that goes on for about 14 years and has released a tremendous amount of energy that covers almost 42 light years of space, which is our universe. So we are lucky that it's there. So that means that when we go to very high energy scales, this kind of quantum gravity effects cannot be forgotten anymore. The universe does not have this kind of continuum, geometrical kind of space that we use at the energies of today. So altogether, these notions may lose their familiar kind of meaning. So, on the other hand, quantum gravity, it is indeed a framework in order to study the cosmology of the universe. There are, to my mind, some kind of fundamental open questions in cosmology, or issues to which we have given some kind of phenomenological, to my mind, a bit of unsatisfactory kind of answer. The first is the emergence of space and time. In standard cosmology, universe comes from an initial singularity. The second is the origin of energy-time exponential expansion, so the standard inflation versus alternatives to the standard inflation. The third one is the fact that we know that our universe is in an accelerated expansion, which means that you have something that takes the form of anti-gravity, that we call it dark energy. We have absolutely no clue what it could be. And then is the issue of the origin of cosmological perturbations, inflation, bounce models, quantum fixations of geometry. There are different kinds of approaches that one could take. So, one has to keep in mind that we have a very kind of, we made a lot of progress in cosmology. We have now this standard paradigm is the Lambda CDM cosmological model. It's based on Einstein's theory of general relativity with 2 ingredients, the dark matter and the dark energy. And here is my comment. Historically, the major breakthroughs in physics have been achieved when someone comes up with a theory based on simple premises of universal validity. For instance, Newton. This universality may later be in question, leading to further developments and new steps forward. Example, Albert Einstein. But I believe that now we need to make one more step. We accumulate more and more data, but we do not have really a theory to explain them. And I believe that science does not get along with many rules like models, we need theories. So, let me start with the first of this set of questions which I put before, and try to see how these questions could be addressed within the different proposals of quantum gravity. So the first is every time exponential expansion of the universe. So there is an enormous kind of proliferation of papers in inflation. If you see how many papers have the title or the abstract, the word inflation, I think there are about 14,000 papers. Despite all this enormous effort and all these papers that have been written, inflation remains a paradigm in search of a theory. So, the onset of inflation is an important question. Do you have really the particular initial conditions so that inflation can start, this kind of curvature dominant? So this we have studied it from many years ago and seems that the universe needs quite particular initial conditions. Now, are these the result of the semi-classical era after the quantum era that we don't know? It's an open question. So, is inflation generic? Is the first thing. The second one, usually this is what gives, let's say that inflation can start somehow. What gives this kind of inflationary exponential expansion? So usually, as we had also before, is done through a scalar field. However, there are important kind of constraints from particle physics because in some models it's difficult to take any of the Higgs that exist, any of the particles, the Higgs if you wish, that exist to play the role of the inflator. And people say, well, it could be another kind of particle in the dark sector, which we don't know. Now, the standard Higgs mechanism cannot lead to inflation unless you have a particular coupling, self-coupling of the Higgs. So I don't know how natural is to do that. And of course, as we heard also before, you can have some kind of modification of gravity. You could have the Starobinsky model, but as I said before, again, we don't know where it could come from. Then there is the Transplanckian problem, which usually often has been put under the carpet in the models of inflation. And finally, you have a whole set of alternatives to the standard inflation. Matter-bound scenario. This is based on the duality invariance of perturbation aspect. The pre-Big Bang scenario, which is an approach to superstring cosmology, I'll highlight some of them. The Pyrotic scenario, which is based on the M theory in 11 dimensions. I will make some comments about what they say. And then, of course, the string gas cosmology as well, which is based on some kind of one duality theory of the string theory, the duality between big and large spaces. So, let me start. Emergence of spacetime from string theory. This I highlighted a bit yesterday when I spoke, on Tuesday, about the ADS-CFT correspondence, the duality between gauge and gravity. So here we have a 10-dimensional string theory, which is equivalent to a 4-dimensional gauge theory. So basically, we say that these are two limits of the fundamental theory which we don't have. So then the question is, then the question is that if space and time are not fundamental, so for what does it replace them, where do they come from? So usually you take that there is a kind of auxiliary space-time metric which is fixed by the boundary conditions which you have at infinity. So the conformal field theory uses this metric, but this is not the physical metric. So strings do not give the metric itself, but actually you have that strings and the space-time that are actually emergent from the conformal field theory. Then you have within this kind of string theory, endless theory, and so on, I would like to discuss the kind of string gas cosmology, which gives you the fact that you do not have the temperature to go to infinity, and also how you can explain the dimensionality of space-time. So let us consider that we have this kind of torus that I saw there, and you have three kinds of modes. You have the oscillatory modes, and in addition in string theory, you have the string oscillatory modes and the string winding modes. There I saw the winding number for a closed loop is equal to 0. It winds around the torus, how many times it winds, you have different winding numbers. So, let me then take a box in thermal equilibrium, which initially has very large radius, which means that the momentum modes that they have an energy that goes 1 over r, will be the dominant one. Okay? The oscillatory modes, they're independent of the radius, and the winding modes they go proportional to r. So then what is happening is that these momentum modes, if your space is large, they are going to be light. And if you try now to see what's going to happen when you decrease the radius, then it is energetically expensive to keep these modes. So what happens, you are going to transfer their energy first to the oscillatory modes, which are independent of radius, and then to the winding modes, which is proportional to radius. So what happens is that as you go to smaller and smaller kind of R, the temperature increases. At some point, where am I going? Here. At some point, it goes to a maximum kind of value, and then it goes down. So like that, you have solved the kind of singularity of temperature, because you have this kind of oscillatory mode. Then the question is, what about space-time dimensionality? So here you say that I start with a space where I have my 11 dimensions, how many you want, which are compact and small. So what happens is because the winding modes have an energy which is proportional to the radius, you cannot expand that a lot because it's energetically expensive. So what happens? The momentum modes now pick up. So the universe starts decreasing in size. At some point, because they go like 1/r, it will be expensive to keep doing that, and you start expanding. So the universe goes through an oscillatory kind of period, which actually explains the entropy of the universe. The universe is old, and the only thing that you need for the universe really to be able to decompactify is to get rid of the winding modes. How can you get rid of that? These are strings, so they move in a two-dimensional worldsheet. So you have these two worldsheets to collide one with the other. How can it be in 3+1 dimensions? So that may give, so a bit, this is a bit of ad hoc in many levels. Also because this duality is just one of the dualities of the string theory. There are many other dualities. So there are many gaps in many of these kind of a bit ad hoc kind of arguments, even though it has been worked a lot, various kind of issues also about structure formation and all that. But I think there are some loopholes everywhere. But anyway, that's a way to go with the string Gas Cosmology and explain the initial singularity and the entropy of the universe and the space-time dimensionality, because this theory per se, it lives in more than 3+1 dimensions. Okay, what's the next one? Okay, the answer to inflation within string theory. So here is something that we heard a bit before, the internal inflation. Once inflation starts, it will never go down. So here there are two mechanisms. First of all, we expect inflation to end because this kind of material, which has to have a repulsive gravity for inflation to start, is unstable. However, this repulsive gravity material has also exponential expansion. But what it has been shown is that the expansion, it will be faster than the decay. So here I have a diagram which I saw. And I start with a repulsive gravity material, and I see how it changes in time, okay, it's in equal sequences of time. Here I do not show the expansion. You have to take that each horizontal is 3 times as the previous one. So the initial repulsive gravity material remains the same. But at every time step, I have 1/3 of that, which makes a pocket universe, okay? So in that way, you have this kind of proliferation of inflationary kind of universe which appear, which might have completely different kind of properties than what their neighbor has, depending on what kind of fields you have, how kind of compactifications you have, and so on and so forth. So then you go to another kind of speculative idea, the famous multiverse. Okay? So the proposal here says that there could also be other big bangs, which might be completely disconnected from ours. And all this kind of universe is what you call multiverse. And there existed different definitions of the multiverse. The first one, which is the level 1 multiverse, which I think all of us, we accept. We don't accept the other ones, but this we accept. Basically tells you that there are other kinds of domains in our one Big Bang that they are causally not connected with us. That's why what we do has to do with the observable universe. And there might be, it's like a Swiss cheese. There might be the other ones which expand, we are not in causal connection. Then we have the level number 2. which says that if there is some mechanism that can give Big Bang, then could give even more Big Bangs in the same space-time. That could be like the case of a single universe which goes through kind of expansion collapse, or it could be an eternal inflation. So this is the level number 2. Then we have the level number 3, because quantum cosmology has often been associated with the many words interpretation of quantum mechanics. Then you can say that every time that you make an observation, a new kind of universe could be branched from there. And then you have the level 4, even more extreme, that says that anything that could exist mathematically probably somewhere exists in nature. And there you have that these regions that have completely disconnected laws, completely disconnected kind of physical notions and so on. So then the idea is that you start with so here you have to take one of the two approaches. You start with a fundamental theory, which is your quantum gravity, which we don't know or we try to build it. And then you have two kinds of routes that you could follow. In the first one, you say that the parameters are going to be uniquely determined there. I have to find how, and therefore there is absolutely no space for an anthropic principle. In the second kind of route, you can allow for any kind of alternative universes to exist, and then you select the one where all of us we can have this meeting, so we go through an anthropic principle. And I think that all that might be a nice kind after dinner with a glass of wine kind of discussion, but there is no way that we can test any of the predictions of the second route. Okay? So you can say whatever you want. So I think that's my personal view, that there is very little room, if any, for multiverse in physics. Okay, so now I would like to highlight this idea of a pyrotic universe that can give this universe from colliding brains. So here you expected that you had higher dimensions. So it's what I was trying to say the other day, that you had a bulk within which you had embedded brains of different dimensionality, depending what is the class of string theory that you have adopted. So let us start with a universe that consists of 5-dimensional space-time, within which you have taken 2 3-dimensional brains. One is the universe in which we live, so I'm going to call it the visible brain. The other is the 3+1 brain, in which we don't live, and I call it the hidden brain. So then I start with the simplest possible situation that the universe is called. It is in this BPS state of string theory, and it is nearly in a vacuum situation. So what happens is, at some time, there is a new bulk brain, so here is an assumption, which has nucleated miraculously somehow, and start moving in the bulk. It starts moving in the bulk and collides with the visible brain in which we live, and it is absorbed. During this absorption, there is a phase transition. Now, you might think, oh, that is speculative. I'm not saying the opposite. Eh? So at that kind of collision, it is absorbed by the visible brain. And what happens is somehow it turns the gauge group of the visible brain to the standard model of particle physics, plus it creates 3 families of light quarks electrons. At the moment that you have this collision, there is some kinetic energy of this back brain which is released, and this release of kinetic energy is going to start the Friedman-Lemaitre Robertson-Walker, a kind of radiation-dominated era. And then there are some ripples of the bulk plane which remain, and then this they lead to a spectrum of energy density fluctuation. So here I have a scenario, this ekpyrosis, a scenario that gives me a Big Bang from string theory. Now, all that are words. In practice, this has put into a model. So here you can see, for instance, the separation between the hidden brain and the visible brain it is translated to a scalar field with a given potential that you can see there. I have an equation of state which is ultra stiff. I need a particular time of duration of that era so that I can solve the problems for which inflation was suggested, and there are a number of predictions. There is no horizon problem. in this kind of scenario, merely scaling various spectrum of curvature fluctuations. However, there are some non-Gaussianities which may be in conflict with the data that we have, and it gives a strongly blue gravitational wave spectrum. So here is another kind of prediction which can falsify this scenario. And then we enter the most recent developments in string theory, which may lead to a disagreement between string theory and inflation, which is the swamp. So here in this plot, what I'm trying to show that there might be many self-consistent conformal field theories, which actually, if you take them in the ultraviolet kind of regime, do not come from string theory. The ones that come from string theory, they belong to the landscape. The other ones, they belong to the swamp. So there are these constraints. The Swampler distance conjecture, which gives an upper bound on the range which is traversed by a scalar field. This is work that has been done by Kumbach and collaborators of his. So it gives me a constraint, okay, in what will be the upper bound of this field phi, which plays the role of, if you wish, replacement of the scalar field. Then I have the de Sitter conjecture, which is a lower bound on the derivatives of the scalar field of the potential. And these two kinds of numbers have to be of the order of 1. So these are the constraints. Now, what are the cosmological implications of that? And if you go to see what is the limit of these values in standard inflationary models, you find that in one case is bigger than 5, whereas it has to be smaller than 1. In the other case, is smaller than 10 to the minus 2, where it should be bigger than 1. And then the result out of that are Swampler conjectures wrong, because after all there are concepts. Is inflation wrong? Are both wrong? And then there is another as well issue about the late time accelerated expansion. So what is this dark energy? And there are two kinds of scenarios for the dark energy. Either it is the cosmological constant, or you have a dynamical dark energy. In other words, you have the field with an equation of state which changes with time. If I take into account the conjectures that I gave you before, then it cannot be the cosmological constant. Then it has to be a kind of dynamical dark energy. Okay? So let me take this idea of the dynamical dark energy. So it has, as I said, an equation of state which changes with time. And let me define by lambda what is the derivative of the potential with respect to phi divided by the potential itself. So in this plot, I show the equation of state as a function of the rest, okay? And I have the different curves in different colors there. They are predicted equation of state for this kind of quintessence kind of potentials with different values of lambda. And then this black curve, okay, is the observational bound that we have from supernova, from baryon acoustic oscillations and so on. So you can see that the maximum value that you can have is this purple one below the black, which is 0.6, which is not 1. So then the question is, the challenge, one has to come up to construct a model which is for dynamical kind of dark energy, which is in agreement with the observational data, CMB, supernova, baryon acoustic oscillation, and so on, consistent with quantum gravity and not in the swamp. And now it seems to be that there is a kind of borderline possibility to be able to do that. So there are some important constraints about the inflationary models and string theory, if you would like to say that these models are somehow accommodated within the string theory as theory of gravity. Okay, so now, so far I think about string theory. Let me move to something else. Yeah, in quantum cosmology. So now I would like to show, you see, I believe that the mechanism of inflation itself, it seems to work. but I would be happier if this kind of mechanism comes from the gravitational sector of the theory than someone put by hand. So let me take now loop quantum cosmology, which is a symmetry-reduced version of loop quantum gravity, keeping in mind that the gap between loop quantum gravity and loop quantum cosmology might be huge. At any rate, it's not negligible. So, in classical homogeneous isotropic background, what we do in cosmology, then what we have, our space-time is characterized by a scalar field and some matter fields. Now, in our case, we are going to have psi is a quantum state, which depends on A. Actually, we do not have a really scale factor. We have a volume. 1/3 of the volume gives us a scale factor. And we do not have time, but we have a clock, which is usually given by a scalar field factor. So we have kind of relational dynamics. So now what I'm going to do, I'm going to take this quantum state psi, which is peak actually in the classical trajectory at late times, and I'm going to take the Hamiltonian constraint to move it backwards in time to see what's happening at the Planck kind of scales, when I have high curvature and density. So what you see is that at the beginning, the wave packet follows the standard classical trajectory until you hit this energy density of 10 to the minus 4 Planck energy density, and then we can no longer forget the quantum gravity correction. So when you write the modified Friedmann equation, there is an extra term there in the right-hand side, rho minus something, and the minus has the good sign, it has positive sign that you were stuck. So what happens is that actually you find that there is a bounce that you are going to get, okay? And the bounce is found when you have the highest energy density, which is what I did there, is 0.41 rho Planck, where it's given in terms of this area gap delta, which is actually the fundamental length scale at which the loop quantum gravity corrections they come into game. So, and then what you are going to have is the densities, energy density is going to decrease, and when it reaches the value of 10 to the minus 4 of Planck, then you forget about quantum gravity corrections and you go back to the standard Friedmann equation. So you have a bouncing kind of solution. Now, however, so here I have to say that inflation, as far as I know, within LQC has been studied with the objection that I raised the other day. In other words, you take the modified Friedmann equation and you put by hand a matter Hamiltonian and you see how it behaves. To me, this is not really very satisfactory. Okay? So the onset, so the inflation through the gravity of your theory, not through a matter field, I don't think that has been considered, or it has been considered. It didn't give any results. I mean, I don't see how it could have been considered. Anyway, so now I'm going to move to group field theory. Now in group field theory, there is a mechanism. I mean, we can actually explain the expansion of the universe, and we have as well bouncing conditions in the absence of the scalar field. So as I said on Tuesday, we have somehow of quanta of geometry, okay, and then we expect that the phase transition took place. Here is an assumption. We have quite some arguments, but we do not have a proof. And then we have a kind of phase transition from a symmetric phase to an asymmetric one, a condensate, once a parameter gets a negative sign. And like that, we are going to have emergence of a continuum space-time from discrete pre-geometric quantum structures. And this is, I said, based on the idea that we are going to have a kind of phase transition and a condensation which take place. So what can we do like that? Because we can play the same game, we can find the modified equations, and we can see what we get. So the first thing that I would like to remind you is I said the previous time that we have to specify what is the gauge group, and we take the sp2, what is the basic constituent of matter, we take a quantum tetrahedron, and then we take a complex scalar field, and we need an axion, which is a kinetic quadratic term and a sum of interaction potential. So this is the model of group field theory that I'm going to start. I want to keep that in mind. So if you do that, Then I'm writing here the modified Friedman equations. What I'm writing now, I have forgotten the interaction term, okay? The interaction term, what does it tell you? The way that you glue this quantum tetrahedra together. Let us say that I don't glue them, okay? So I do not have interactions. So here, in general, is the modified Friedman equation, where, remember, I said that I take a complex scalar field. The modulus of this complex scalar field is what I call the rho, and the V is the elemental volume of my tetrahedron. So this is the emergent Friedman equations that we're going to have. M is a parameter that you can fix from the parameters of your theory, and E is what we call GFT energy. I mean, I can give you the expressions if you want. And then what we have found that no matter what is the sign of this E, you are going to have a bounce. So there is a bounce. So again, I have a bounce in cosmology, which means I can solve the initial singularity. So at high kind of values, you are going to have a plateau, but then as you go to smaller and smaller kind of this corresponding G, which now I have not written it, I mean, actually I have written it, but you cannot read it, is this expression there, then you can find that in both cases, plus or minus E, you have a bounce. So here there is a bounce. Okay. Then let me turn off the interactions. So you can see I turn on the interactions. So in other words, I have this kind of polynomial expression with different parameters of B, of W, and N prime. Okay? And what you find now that I have glued this quanta of geometry, I have found that the bound solution exists, but I have oscillatory kind of case. And actually what is interesting to find is that depending on the value of these three parameters of this interaction, I can have early stage of exponential expansion. So here I make a comment. We have shown that if we forget the interaction, the bound solution exists. If you put the interaction, this bounce gives to oscillation. Inflation cannot exist, so early exponential expansion in the absence of the scalar field does not exist if I don't give a particular interaction between this tetrahedra, which for me is very interesting, because that means that I give you a prescription how I have to glue this quantum geometry in order for this space to give an early accelerated expansion. And then you have to go back in your fundamental theory to see if indeed there are some kind of justification why you have to pick up this kind of values that I have given there in order to be able to give not only to give exponential expansion, but it can last as long as you wish. So, in other words, I give a prescription to my friends who do GFT from GFC, how they have to model it so that I can have a cosmological model which is in agreement with the data. And then we went a bit further than that. Up to now was a complex scalar field. Then we said, well, if I had a theory with a real scalar field, could that work? And the idea is that yes, provided this energy is negative, remember before positive or negative, the result was the same. And then we'd like to see what happens if you try to evolve the system. In other words, if I'm going to run it with my clock, I don't have time, I have a clock. Okay, so what we found is that in the case that your system is isotropic, then we can get continuous, homogeneous, isotropic free geometries built in this way. And it's very interesting that if we start with anisotropic background, as the rotation, the relational clock goes on, then the anisotropy disappears. So I can get an isotropic kind of cosmology, if you wish, and this anisotropy does not stop the kind of bound solutions that I had found before. So all that to say that within the group field theory kind of models, we're able to give a prescription that tell us how we have to glue this quantum geometry so that an early enough accelerated expansion can take place. So now what is that? Now it's causal sets. So I give you only one prediction I had from causal sets.
Just a very elementary question
Yeah.
about the. So in the in the loop quantum cosmology, those were sort of quantum cosmology equations, but in the group field theory, you're working with sort of classical.
No, it's not classical. It's not classical. I wrote down an equation which is generic and a condition for inflation which is generic even in the absence of a scalar field. So instead of talking of scalar fields, I talk about volume. And then the equation that I found is again a kind of modified Friedmann equation from the corrections that come of the group field theory. I write this action that I gave
that
before.
Modified Friedmann equation, that's just
No,
a classical equation?
no, I don't apply. No, is a modified Friedmann equation. So I found the evolution equation that I get from that action.
But it's not an equation for a wave function in
No,
space.
no.
It's classical in that
Is
sense.
it, yeah,
Okay.
in that sense, yes, yeah. Okay, so the causal sets. Now, whereas I have worked with all the other things that I'm discussing, with causal sets I have not worked, okay? So for causal sets I just know one kind of phenomenological prediction. I don't think that there are many more. So anyway, the question here is about the dark energy. So the point is that, or cosmological constant, or whatever you want. So the idea is that we know that we are in accelerated expansion with a component that should be about 69% of the energy density of the universe, and that today the value is 10 to the minus 122 units of Planck. However, if we take any kind of quantum field theory that we want, then this value should be of the order of 1. So there are about 120 orders of magnitude gap between the two. How this can be resolved? So there is again there are some loopholes, but there is an argument that was put I think by Sorkin about this stuff. So you assume, and this assume should be with capital letters, you assume that there is somehow some unknown quantum gravity full theory which drives the value of lambda to 0. If that's correct or not, we don't know. This is an assumption. And therefore, you have that the observed value is just a fluctuation around this kind of lambda equal to 0. Now, fluctuations in the value of lambda, they should be subject to the uncertainty relation between lambda and the conjugate variables, which is v. So, you are going to have d lambda should be of the order of 1. So, now it comes the ingredient of causal sets. Causal sets, if you remember from Tuesday, there is a relation between n, the number of sets, and v, the volume. And you have Poisson fluctuations, which tells you that there will be this kind of relation, the square root of n is related, which gives the fluctuations from the Poisson statistics that you have of the number of elements. Here is the relation between n and v, which is exactly the distinctive feature of causal sets. It should go like square root of v. And therefore, if you consider what is the volume of the observed universe today, you can find the 10 to the minus 122. Now, if you buy this argument or not, I leave it to you. But that's the only, I think, predictions they were very proud of. There are some loopholes here. Huh? So this is what comes here. And then I'm going to move to the non-commutative geometry. So remember what we said last time, is that you have the product of the four-dimensional compact Riemannian manifold with an internal kind of non-commutative space for the standard model, which is given from the choice of the algebra, the Hilbert space, and the Dirac operator. You then apply the spectral action approach, which says that the action is going to depend only on the trace of the Dirac operator and normalized by this value lambda, which means I take all the eigenvalues of the Dirac operator, which are smaller than a given cutoff. You do an expansion in terms of heat kernels, and you have these quantities which are going to appear, F4, F2, F0. Now, the F0 relates the constant couplings at unification. So then what we did, we said, let me take this background and go to study tensor perturbations. And I'm going to find therefore the propagation of gravitational waves. I'm going to compare them with binary data that I have, and we were able to put a constraint to this parameter. So inflation again here I don't know how to solve it. Here, instead of coming back to cosmology, what we did is that we use cosmology to constrain three parameters of the theory. So always I talk about this kind of intimate relation between these two things. And then came the gravitational waves, okay? So here we're able to put constraints in the theories. Particular, you know, it was the gravitational wave event W170817, which was followed 1.7 seconds afterwards with electromagnetic counterpart with gamma ray burst. So therefore, we were able to put constraint on branes and extra dimensions, okay? Because it's going to be a damping of the waveform due to this gravitational leakage to the extra dimension you have, to your back. So there is a relation between H, which is the strength that your interferometer is going to read, and the luminosity distance of the right, which you get from the electromagnetic counterpart. So, like that, we find consistency with GR in 4 dimension, and some string theory models, like the Dvali, Kapadace, I can never pronounce it, the polarity was ruled out. We put some constraints in extra dimension, so that was helpful. Then there is also the fact that you say, well, if I have a kind of different theory, like, you know, like Horava ellipses, like double special relativity, like massive gravity or whatever you have, then I don't consider the formation of the gravitational waves, but I consider the propagation, okay? So the dispersion relation is going to be different. So instead of being E equal PC, it's going to have an extra term. So this extra term has been studied, has been modeled phenomenologically by this APC with the value A and alpha, which takes different values depending which kind of gravitational theory you want to consider. Okay? And by doing that, what you see is finally the phase of the gravitational wave, which I write it, you see the gravitational wave in Fourier space H, I write in terms of the amplitude A, and the phase is going to have an extra contribution, and then constraints were put there, and you can see on the right, then you can pick up your theory that will give you a particular value of alpha, massive gravity, Horava ellipses, whatever you want, double special relativity, and you can constrain it, and in addition, there was put a constraint in the mass of the gravity. And the other thing which was very interesting, we were able also to put constraints on pure quantum gravity theories. How is that? There is a generic kind of ingredient in all quantum gravity theories, which is the dimensional flow. Okay? The dimensional flow. So the dimensionality is not fixed. So then, what we did, we found a relation which again compares what is the strength that you measure with LIGO and what is the luminosity distance that you get with gamma ray burst or whatever electromagnetic kind of counterparts experiments you have. So this expression there, you see there is this small gamma. This small gamma gives you the energy state at which quantum gravity corrections are important. And you have the UV scale, which is important, and then you have an intermediate scale, which is not dominant but cannot be neglected. And then you go to the literature and you find, I mean, for Kaplan-Minkowski, for stellar gravity, for loop quantum gravity, for spin forms, for quantum, from non-commutative field theory, for causal dynamical triangulations, the values exist. And then we took LIGO data and projected user data, and we said only group field theory, spin forms, or loop quantum gravity can generate a signal that will be detectable with gravitational waves. Now, I want to emphasize something, not to give the wrong impression. I'm not saying that only one of these three theories is the correct. They might be all wrong. What I'm saying is only these three theories could be tested with electromagnetic counterpart. That's all. Then you have to go back and try to form, this kind of signal that you want. So that was an interesting thing. So what else? I think I'm going to the next. So my conclusions, before I give the comments, is that there is a variety of cosmological models which are inspired, not direct consequence, but inspired from quantum gravity proposals. These are not theories either. So this is going to help us. On the one hand, to test the validity of quantum gravity proposals, on the other hand, to somehow address in a more satisfactory way some of the open questions or phenomenological kind of cosmological models that we have. So, what I'm writing here? Okay, so some personal thoughts about that. There are, as I said and I summarized, there are some crucial ingredients that in all of these quantum gravity proposals have to a less or a bigger kind of extent put by hand, like the Kelvin string theories model or what we discussed, the mounted non-perturbative approaches of quantum gravity. There is the open question, how strong and intimate is the relation between the simplified cosmological model inspired from the yet unknown full theory and the full theory itself, when we say that we rule out the theory or not. Then I believe that the landscape of the string theory to me is not a prediction, it's not, for me, it's a pathology of the theory than anything else. Non-commutative spectral geometry, as I presented, as it existed, it lacks quantification. So again, quantization. So again, there is something that is a problem here. And therefore, my belief is that probably all these theories are wrong, or to some extent incorrect. And I think that the reason for which most probably we are unable to build a theory of quantum gravity is that we do not have mathematics. We use the same mathematics we discussed over a walk yesterday. We use the same mathematics that we use in, Morzine, path integrals, so the standard things that we use. But I believe either a new tool has to be developed from mathematics for assisting physicists, or already exists and we're just ignorant and we don't know it. But if we go still ahead with just the same tools that we have around, I think that probably it's not going to be successful. Thank you very much.
Thank you very much, Mairi, for that talk, and I particularly appreciate we have sort of had a concrete call to action there in terms of so questions. Yes, over there.
Did I understand the slide on the dimensional flow correctly, that you are actually able to see signals of the spectral dimension at high energies in the cosmological data, so that you could rule out different theories based on whether they have the correct spectral?
Exactly, because we have studied, it's quite technical, but I can show it to you. We have shown how it will be the modification of the propagation of tension perturbations, which are gravitational waves. And they have this kind of signature that depends on this parameter gamma, which is related to the spectral dimension. And this is generic for the quantum gravity kind of theory. And then the particular value depends on which theory you take.
Yes, precisely.
Modification is generic, yeah.
Because I guess in quasi-state theory it would be 2, and in quantum gravity it would be 0.
Yeah,
exactly.
So there is a list of all these values, what they are. I mean, at the beginning, naively, you can say, well, everything is going to be diluted by the Planck scale. Then you find that this generic thing that modifies things and has the same kind of general expression like what we've seen in the case of extra dimensions. Also, as I saw, is this difference.
You have this worry that you don't like when matter is put by hand into the theory of quantum gravity, but I have the feeling that matter is put by hand in general relativity or in cosmology, like you just had
but that's not a theory of quantum gravity, it's general relativity or cosmology.
Well, but they are
it's at a much lower scale. Now I would like to find a theory that explains me all that. So if I have to find a theory that explains the right and left hand of Einstein's theory in a more unified way, then I cannot do it.
But we're happy with it.
You're happy, I'm not. We discussed about that before. You keep saying I'm happy, and I'm saying I'm not. You told me you're happy with similarities as well. I'm not. So, it's there is a preference. There are people who are happy with the anthropic principle. I'm not. So there is space for all kinds of taste.
No, I think it's the feeling in the loop quantum gravity community.
No, loop quantum gravity, I said it for one probably last time. You put the matter Hamiltonian by hand. This, I don't think that is anybody, even the people, I think if you go to talk to Abai as well, he would agree with me. The point is that they don't know how to do better. I don't know how to do better. I don't criticize, I do not have a better way of doing it. But I'm saying, is an unsatisfied, I cannot study, I have studied that, I have a paper of that, but it's not that because I did it, I say, we take inflation and we just put it in this context. We don't solve anything. We say, if there is the inflation, they could behave in that way. But I'm not saying that this is an intrinsic kind of element that could be, if you want to do a full theory of quantum gravity, that's all.
Thank you. I'm interested, it's a factual question about inflation as it comes up in group field cosmology. Does this also lead to eternal inflation?
No. The only thing, as far as I know, in LQG that was found was the bouncing model. You have a bounce. But it's exactly the same thing that we said. It has been studied, the behavior of an inflaton field put by hand in the context of the modified Friedmann equations.
No, but I mean group field.
Excuse me, group field theory, I'm sorry. Group field theory. Group field theory, we found that if we glue in a particular way this kind of tetrahedra, then we have a dynamics which gives inflation. And now, as far as, I don't know how to say something stupid, I don't remember exactly, but I think we saw, that goes back some years, that there are some tensor modes of quantum gravity that they favor this value of the parameters that can lead to. So what we saw is that if I forget the interactions, what I find a bounce, I find deflation, but lasts extremely short time. If I put interactions, any kind of interactions, I found this oscillation, and now if the interaction have a particular form, the polynomial is particular values, then the inflation can last as long as you wish. So now you have to go back to the group field theory and say, how can I build a group field theory model, not cosmology, theory model, with this kind of interaction? But this is not my expertise of that. So here is where is the question.
Thank you.
You're welcome.
I think.
Oh, sorry. Go ahead.
No, students.
Probably the question is the same.
I agree with your concern about matter being put by hand in models, and I agree that we should look in general beyond theoretically string theory for ways to make matter emergent in whatever way that means. But I'm also concerned about how, at least if I understood correctly, because I'm not a huge expert in string theory, how in this Pyrotic Universe scenario, I also find that this hidden colliding brane is also, even though you have an inbuilt way to make matter emergent in your string theory, I still find that putting a hidden brane is kind of putting something by hand that will later generate.
I didn't say the opposite. If you remember or pay attention to what I said, I leave it to you if you believe it or not. Okay? So that's what if you buy the extra dimensions, then within them theory you have the bar within which you have embedded branes of any dimensionality. Now, within all these branes of different dimensionality, there will be some of 3 + 1 dimension. One is your universe. Fine. The other one of the same dimensionality is called hidden because it's not your universe. That's all. Now, if you buy the fact that you have extra dimensions, all these branes, they can move. As they move, they can collide. As they collide, these mechanisms can exist. Now, I think I repeated more than once that this is again a model. Whether it explains the nature of which we live, I don't know. Not that I buy that and I take it with no criticism. I mean, it's as ad hoc as anything else. But if I get the impression that this is free of any error, then that's not the case.
No, I was just mentioning that it seems a bit misleading sometimes to highlight that matter is indeed emerging in string theory, because at least in
No, I didn't say there that matter emerges in string theory. It doesn't emerge from that. I said it from the ADS-CFT. For there, I didn't say because the whole idea of these brains is that all the matter fields already they live in the brain, and then you have gravitons that go everywhere, and that's why gravitation it's weak, because propagation is in the back. This was a mechanism just in order to say I can provide a way for the hot Big Bang through the collision of two brains. Now, with the caveat that I said about blue spectrum and about non-Gaussianity. So there is what is, if you wish, good, let's say, quotation is that gives some predictions that seems to be in conflict with the data. So it might be the whole thing out.
It's not a comment.
Oh, another question. Go ahead. Yeah.
I was wondering, so in the swampland,
I cannot hear anything.
in the swampland conversation, sometimes you hear comments to the effect of we might be able to find a particular island within the swampland, like a small island with just a few viable inflationary models, and then some alternatives are, well, we're trying to stay clear of the swampland altogether and be firmly within the landscape of models. And I was wondering if you have an opinion on, so you set this up as sort of cosmology and quantum gravity feeding off of each other, or sort of jointly constraining in research. Is it better to be able to find a particular inflationary dynamics that happens to avoid constraints, or is there something more satisfying about sort of staying clear of the conjectures, being as far away from their violations as possible?
So, sorry, so you say whether it's more satisfactory to have a small island of swampland idea, which is in agreement between swampland conjectures and inflation with respect to the data, or is better to just look? I think that anyway, it's always possible to find a tiny island that is going to satisfy your conditions. The point is how generic this it is and what the conclusions out of that. For me to find a small island that fits the data, personally, is completely uninteresting. But you know, as I said, altogether there are, you know, here in this swampland idea, there is again a criticism. There are constraints about these conjectures and the constraints actually on the potential of the inflaton field. But this does not address at all where on earth this inflaton field comes. So my big concern goes there. Is not if I can somehow, you know, cook the things to be in agreement with the data. Already, like what we said before for the reheating, this is a detail, you can fix it. The question for me is more fundamental, and I have not seen that to be addressed. Apart this model that we just discussed with the brains and all of this. So, yeah. Or these dualities that again is one duality of all the dualities that exist that has been studied. So there are loopholes there, but I believe they are more crucial than find a small region that satisfies, you know, all the tests. I think this could be done, but for me, it's not the basic kind of scope. And that's a personal opinion.
Thank you.
Yeah.
Next door.
So maybe a little related in some way to that. So I'm kind of I'm interested in the various sort of experimental observational tests, observations that might put constraints on quantum gravity theories. How that that you were talking about, how that relates to what Chris talked about at the end of his talk, and about the Transplanckian censorship hypothesis. Because that seems to put restrictions on the possibility of observing physics that sort of depends on Transplanckian sort of quantum gravity physics. So are any of the results that you're talking about, or any of the possible kind of phenomena that you're talking about, in conflict with Transplanckian censorship? How are they not kind of probing below the Planck scale?
Well, I think that the Transplanckian that is in conflict is about inflation, is about the perturbations of inflation, because the perturbations have been studied always to some extent classically, and then we say, but at these scales, there should be Transplanckian. So that is the issue. But what I have discussed, as I said, I think, or Marcus, as the question is that for the propagation of gravitational waves, this is not the case because naively you think that it's hidden from the Transplacian, but because you have this kind of issue with the dimensionality, then you can solve that there is not Transplacian issue that shows there. I think the Transplacian has been basically studied in the context of inflationary perturbations, no? So that's why it has been seen, and because you take it a fully quantum origin, the fluctuations of the inflaton field, but you study them forgetting this kind of Transplacian signature. So
okay, but some of the but there were a couple of phenomena you talked about that were assuming inflation, right? For some of the parameters there.
When I said the spectrum, or when I saw about the gas, yeah, I mean, already if it gives an issue, I don't know whether this has been resolved in this context, because there are issues, there are models of inflation where the Transplacian issue has been studied and has been shown by the authors that it's not a problem. Depends on which model of inflation you take, but I have not worked on that, and I mean, probably in that paper by Martin and Robert, this is in more detail. There are not all models of inflation which have this pathology, but even if I neglect that and see that gives me Gaussian perturbations, and Gaussian perturbations has not been found, then already it's out. I don't know. You see what I mean? So it's true that the Transplacian issue for inflationary perturbation is a problem, but has not been seen in all kind of studies of people about inflationary perturbations, either because they don't believe it or because they don't, whatever.
Does that issue have any bearing on any of the phenomena that you were talking about here?
I don't. I mean, if anything, it's going to do them even worse. I don't think that it's going to facilitate to make them to pass the test. So I didn't speak a lot about in the case of LQG or LQC, I did not talk about that at all. I said about bouncing scenarios because I said the matter field is put by hand, so I don't believe it to be very strong. Then for a GFC, I talked about inflation, not the growth of perturbations. Again, because I'm very reluctant about how you are going to do the growth of perturbation there. I think we need to understand better the background before we perturb it. So therefore, the issue of perturbation theory does not appear. In non-commutative geometry, I said nothing about that because I don't know how to do it. In causal sets, there was nothing about that. There was about the value of lambda. And then what I said was the propagation of tensor perturbation. So again, it doesn't enter this mechanism at all. It could enter in the discussion of brains. I don't think that because there was the perturbations, But the whole thing is a bit too ad hoc now. I'm not sure how well is this kind of, they took the separation between the two brains as a scalar field, which plays the role of the inflaton. And then they wrote down a kind of potential. Where does it come from that? I'm not very convinced. So already, there are some open things there. So I don't know.
And I guess there was the string gas cosmology as well, but is that just a prediction for the
For the string gas cosmology, because I believe that there are some open questions about the perturbation in string gas cosmology. I did not discuss about that. I discussed only about the dimensionality of space-time and the temperature singularity. There has been a lot of work by Robert et al. On about perturbation theory. As far as I know, there is discussion in the community, so I did not mention that. Okay. Well, also, I tried to some extent to discuss more about things that I have worked as well, because I would prefer not to talk too much about things I've never done anything. Then it becomes more.
No, but that was super helpful kind of answer to see how this fits together. Thanks.
Could you say more about why the relation between cosmological quantum models and full quantum gravity is uncertain? In particular, in what and GR.
FLW and?
And GR, right? So in this case,
And what?
And General Relativity.
yeah,
What?
GR.
No, but it's clear, because FLW is general relativity solved in a homogeneous isotropic background, which is the Friedmann-Lemaitre-Robertson-Walker universe, and therefore the relation is, that's it. I take my equation and solve in a particular background, infinite relation. I mean, not even more, I mean, it's the same thing. Now, what I'm saying is that I take a kind of cosmological model inspired from quantum gravity proposal, and then I study the cosmological consequences. These are related to the mini superspace model that I took. How this mini superspace model is related to the full theory is an open question. For instance, LQC is a symmetry reduction of LQG. So what I find from the LQC cosmology, I'm not sure whether actually characterize the full field. It characterizes the constrained space from which I pick the symmetry reduced cosmological model. But I cannot say the results of the LQC are valid for the whole of quantum gravity. That's all.
Okay, so we are not even sure that these are solutions of the full,
No,
the equations of the full theory.
There's no solution here. I take a model, and I say from that model, I'm going to constrain myself to a subspace of that model with some symmetries, and I'm going to study the implications of that. Now, this is a subspace of the full one. Whatever I find is valid here. I cannot say that I have a prediction for LQG, the full theory. I cannot say that I have a prediction whether boundary solutions exist in all space of the quantum gravity. I found it for a subspace. That's all I'm saying. There is a gap between the still unknown full theory and the inspired model from the full theory. I think it's clear. I think it's clear.
Yeah, I was just wondering about the last comment that you made on the mathematical tools. I know it was super speculative. I was just wondering, do you have like an idea what we could take as a starting point? Like
I know, if I had an idea, I could be in Stockholm right now. No. But what I can guess is that probably we should. I don't know. You know, there have been, as we all know, there have been developments in mathematics to help physicists like calculus. There have been other things completely dependent. Here, I think that we need some tools. I don't know which ones, but we go along with what we use in standard GR. I think that probably the problem may be there. I don't think that it's a very wild guess to say that we don't have the tools, and the tools cannot be the standard one we have been using in theories or whatever so far.
I was just thinking, like, usually when this happened, there was some experimental data which...
No, experiment is not going to help of that. There's nothing experimental here that's going to help. I mean, here we need something to formulate theoretic theories. It's not experiment. The experiment tells us, the experiment is black holes themselves or the very early universe that tell us that something we don't have the tools to address some extreme situations that exist in nature. So we need to find different theories to model them. And these theories, they need, I believe, different tools, which are mathematics. And I'm not sure that we have. But that's all I'm saying. You know, that's why I wrote it as a last thing. There's not much we can discuss. I mean, probably we have mathematicians here. I'm sorry if any of you is pure mathematics. I studied pure math me originally, but this doesn't help. So we need people who could have, we can tell them the problems we have, and they could, I don't know, because maybe can come with all the young people who are here. I don't know. But I think this is an important kind of, I don't have an answer. If I had an answer, but it may be a real obstacle in the matter, I think. Yes.
So related to that, is it your worry that in terms of the theory space that comprises all the sort of possible quantum gravity theories, we're really searching in a very sort of narrow part of it in a certain sense because of the kind of resources we currently have available. So then my question is relating to what Karen talked about yesterday, whether certain principles are restricting us to search only in that area, so that is it the absence of mathematical ability, or is it really because we've sort of stuck with a certain way of thinking about our physics that makes us investigate only this very narrow place in theory space?
I think both. Because you know, it's what we do always. We just try to extend our knowledge, which is both local in space and time. To everything else, we have no clue using the same tools. So we have a kind of, a mind that goes along the same tiny area we have experienced. We're using the same tools. So I think they're both combined that might help. That's why I'm a bit pessimistic. But if I say that now, all the quantum gravity people will be against me. That I think that probably none of these approaches is going to be the final one. Also, there is another thing. I hope I'm not still registering what I'm saying. But I think it's also that all these different communities should talk more to each other, because there are common things which exist. So they should talk more to each other and then enlarge it to the neighbor stuff of mathematics to see what could come from there. But I think from what you say, I agree that I believe both are combined, both they put an obstacle. But it's also true that we cannot do much better. So we learn something with this approach. It's not that I waste of time, we learn something. But I think there is still quite some way before we have.
Right, because that would be my follow-up. That Karen seemed to suggest we should search for more principles, whereas you might be interpreted as saying that we should get rid of principles instead, because that might increase our
Yes, I fear that our principles might be biased.
Yes.
So then we stay in the same region of this huge space that we explore, and we will never find something out. But what I said now is very easy to be said. I'm not sure how easy it is to go beyond that. So because all we're educated in the same way, we learn the same principles, how we can get rid of them after. But could be an obstacle. I hope I did not somehow, gave the most negative view about the progress in the field.
I mean, this was also sort of a bit inspired by some things that Chris said earlier. So the different phenomena that you were talking about here that might sort of constitute I can't remember what you said, the test bed for quantum gravity was the way you put it.
Right.
So some of them seem a bit more like, sort of predictions that might be sort of confirmed or disconfirmed. Some of them seemed, kind of ways of ruling out regions of parameter space. Some of them seemed like sort of phenomena that might allow us to sort of set values for parameters. So it's a sort of broader question about, what kinds of scientific tests are sort of going on here, what you mean by a testing bed. So which ones of these are predictions, which ones are sort of ways we just might get some parameter fixing, things like
not
this.
all of them give predictions. From my personal point of view, I would like a kind of proposal that gives a satisfactory answer to some big questions. So, for instance, if I found a way that can explain the hot Big Bang, to just give an example, can explain the early inflationary period, I would be willing to do the next step and see the predictions of that. If there is no prediction, I would abandon it, because it's not physics. I cannot test it. It's the same thing that we said with the multiverse. I can never test it, so it's of non-interest. So I think the first thing would be, can I explain? Can I find a way to model things for which the current state is a bit unsatisfactory? And then the next thing is to give a prediction of the theory. But then there is also a mistake that we often do. In order to find the prediction of the theory, we run a lot, we make many assumptions in the between. So then we find the prediction, which to my mind, I'm not sure how confident I am for this prediction. So there is still, I think, a lot of gap to fill before we find the predictions. But the ultimate thing is to have an explanation with a kind of way to falsify this model. So I need a prediction. I don't know if I answered your question.
Yeah, I think that's helpful, but none of these things on the table do.
Not all of them
all
can.
the big
No,
things
no,
that
no,
you
no.
want, right?
They cannot do it. They cannot do it. Not all of them. First of all, because this is current work that has been done to that kind of level, and then probably not all of them have the ability. For instance, if we take the GFT, group field cosmology, where I work, okay. Now, what could be now the prediction? The prediction could be something for density perturbations, or for gravitation, or for something of that sort that I can find the prediction. I think that still there are issues to be addressed for the background before I go there. So already I found something that helps me, because I found, as I said, bounds, and I found inflation. Now, I should go back and say, for me the inflation to work, I need these parameters to have these values. Could you, from the full theory, could you have any guess about that? Could that be possible? If these people tell me, no, there is no way, then I abandon the model already. There is nothing. I built a model that to work, it's ad hoc. If they tell me, yes, it could come from I don't know which way, but let's say they tell me, and if I'm sure how the background, which means how Friedman equation really, if I have a full control, then I have to go to see the perturbation. So the perturbation will be what? From my point of view, will not be through a scalar field, because then I lost everything from my point of view of the theory, but I would like to see, now I say something very naive, I never did it, to see if I could have some deformation of this geometry of space, and see how this perturbation could propagate somehow, to see if I can find something. Now, this, how I do it in practice, I don't know, I never did it, but I know that there are people who try to do things like that through matter fields, and then I'm not very happy. So not all these theories have been studied to the level of predictability.
I had a kind of, this, from what you said about multiverses being in principle untestable, but my worry with that kind of, if I'm not sure in what sense I believe that they're totally untestable, in that if the multiverse is an untestable consequence of a theory that does have testable predictions, is there a reason why we should remain skeptical? Is there a way in which we can be skeptical about the other multiverses but keep the other aspects of the theory? If there is some kind of testable predictions, which when you then have the full theory implies multiverses, I think I struggle to see how that's as a general thing rather than specific cases, as a general reason why we can't believe in that as a consequence, as in the same way that kind of outside the observable, the fact that there's stuff outside the observable universes and kind of a consequence that's in principle, even in principle, unobservable, but there's a sense in which...
No, I think your question goes to, multiverse is related to the landscape, right? So your question is, if I buy the whole string theory with the landscape, makes the things the 500 and 1,000 kind of vacuum, which could be in agreement with multiverse and could be in agreement with the Feynman inflation, or because I cannot test that, I abandon the whole string theory that gives me this vacuum. This is the question?
I don't really know anything about...
No, but I don't understand your question. You want me to compare what? Because multiverse is something which comes from a theory, comes from this kind of vacuum. So that's your question, or what? So let's finish before you...
I think about it quite well.
I don't understand your question. If you
in a
could
possible
formulate
way.
it somehow.
I guess I think about more in the quantum mechanics case, that kind of basic is if you have a theory that predicts everything you see, but when you look at the mathematics of it, you end up, in the sense
There
of
cannot
the
be
average
theory that
prediction.
predicts things where the mathematics that don't work. I don't understand. So you say the theory predicts but the mathematics.
So you've got a mathematical theory that makes predictions that are extremely successful.
Mathematical theory is not going to be physical prediction. What do you mean by mathematical theory? What do they put it with context? I don't understand. Can you give me an example? I don't understand what you mean in mathematical theory can give some predictions. Mathematical theory will not give predictions in physics.
I think perhaps the question is, if we have a theory that's very good in terms of its predictions about what's observable, and it also predicts the multiverse stuff, could it then be rational to come to believe in the multiverse even though we can't directly observe the multiverse?
No, I mean, look, give me this theory and then we discuss. Because I think
It's read quantum mechanics. You read quantum mechanics.
no, the quantum mechanics, you have the main interpretation, and then you can say that you have a new thing that appears everywhere. This might not be the universe in which we live. This is not a quantum gravity theory. This might not be the universe in which we live. I try to find a way to model the universe in which I live.
But my question is that if you say that in a very, very speculative sense of saying that multiverses do not have a place in physics, it seems like if we could have
No, there are 4 levels of multiverse. I said the first one is not controversial. We all agree. Why? Because we have the cosmology. If I go beyond that, then for me, I cannot test it, so it's not physics. That's all I said. Don't take any kind of extrapolations beyond that. I said a prediction which I cannot test is not physics. It could be philosophy, could be after being a chat, but it's not physics. Actually, what we have been doing, all of us, for decades, was not physics. When we have been playing for ages with scalar fields, and we have never seen a scalar field, when we have been assuming the FLRW kind of background, without having any data that is homogeneous and isotropic, we have been criticized by the whole rest of the community that is not physics what it is. Once we found the scalar field, once we found the isotope with the CMB, then we know that the basic assumptions of modern cosmology were robust. So then we're accepting that we do something that is physics. So there has to be a difference. I can have a model, but it should explain the universe in which I live. That's the basic.
I think David has something.
Yeah, I mean, just wanted to ask about this issue that simply by virtue of being a multiverse theory, something's not testable. I mean, if I think about something like Weinberg's prediction of the value of the cosmological constant, I mean, you can debate whether that prediction was well argued for, you can debate whether it's met, but it's an empirical prediction that was made from a multiverse theory.
So I don't. So what is the question again?
Well, I'm querying why it should be that just because something is a multiverse theory, thereby it's not testable and therefore not scientific.
No, I'm not saying that everything is non-testable, but I'm saying these ideas of multiverse, which, if you remember when I put the transparency, came as a result of string theory's kind of approach with the landscape and the internal inflation. This is not testable.
But I'm saying I'm not sure I'm seeing the argument for that. I mean, again, Weinberg makes a specific prediction off the back of multiverse. Why doesn't that count as a testable prediction of multiverse?
What is the prediction again that you meant?
That the cosmological constant will be no smaller than is anthropically necessary.
But it's not a prediction. It's not a I mean,
it gives a number.
Yeah, you play with probabilities. I hardly believe that this results for. Is
But
all
now
this
we're moving
probabilistic
from
theory?
We're moving from discounting predictions to I don't like the predictions with methods.
To me, it is an anthropic principle kind of attempt to give the answer, and this probabilistic theory that people have been playing about the universe, I'm not very, and I don't think that it's only me. I'm not very convinced.
Sure, so this might be legitimate. I'm just saying that it's one thing to say multiverse theories cannot be tested, and it's another to say I find some of the methodological assumptions that other people use in making testable predictions for multiverse theories not satisfactory.
No, because for me, the way that this multiverse prediction of value of cosmological constant has been tested, I don't buy it.
But now you're saying I don't buy this prediction. That's very different.
But
new
to
predictions
give you
can be
one
made.
prediction of the model, and I say that the model cannot be predicted. You tell me there is a prediction of the model, and I say the way that this prediction has been achieved does not convince me. So there is no prediction of the model. I don't see other.
Very quickly, one last question from me.
So it's more like a comment for the question that Nick had, and then your reply that somehow you trust, I guess, the quantum gravity theory once it was able to predict or to explain better what happened at the early universe at the lower energy scales, right? So I have here like Mukhanov's book on the thermal history of the universe. It's like a nucleosynthesis happens between 200 and 300 seconds, which is like 10 to the minus 5 GeV. then the scale that we reach at the LHC, which is about 100 GeV to 10 TeV, would correspond to 10 to the minus 10 seconds in the history of the universe. While of course the Planck scale is 10 to the 19 GeV. So between that scale and the LHC scale, we have pretty much like 16 orders of magnitude of difference, at least. Now, when I think about like explain the table or where we are, I don't ever expect to rely on the theory of the nucleus of the atom at the Fermi scale, which is 10 to the minus 15. I mean, I have no idea how I would coarse grain that theory to recover like solid objects or condensed matter physics. So I wonder if this requirement is way too strong. Like we don't ever ask a theory to explain phenomena of scales of 16 orders of magnitude higher up to give us some confidence that the theory is actually reliable. So I wonder what comment you'd have about that.
What, if I understood correctly, your question, which I'm not certain, the idea is that I go beyond the theory that I can test, but what they expect that this theory is going to give me some low energy predictions that I can test. So, for instance, just to give you phase transitions at the touch scale or whatever, we cannot see. But we know that if they took place in the universe, they produce topological defects. These topological defects, they should have this kind of dynamics, and they should leave a kind of imprint in the universe at the last Cartesian cycle that should be like that. So then I can never say that my original theory is correct. I can say it's not wrong. So that's what we try to do. We try blindly, with some experience we get, to form a theory at a scale where we could not direct experiments, to see the predictions at the lower energy scale, which will allow us to say, yes, it could be correct, or it is wrong. But we can never say, yes, it is correct.
Great. I think we now have time.